Okay, this is a review of some of the concepts regarding electric fields. And I just want to start back with thinking about what we were originally talking about with electric fields. If you have a charge here, and you have another charge of the opposite sign nearby, we talked about the fact early on in the semester that if they're opposite signs, they're going to attract. If they're the same sign, they're going to repel each other. This concept, so if this is a plus Q charge here on the left and a minus Q on the right, or vice versa, it's going to be attractive. This concept underlies the fact that without this charge here, this single charge here would be generating an electric field that radiates outward if it's a positive charge, as far as its electric field lines, which we represent like this. And that gives you the direction that a positive test charge would experience a force if it were located at that location. Alright, so etc. I could keep drawing these depending on the number of charges, field lines that I'm representing per unit charge. But if this were a 1 microcoulomb charge, for instance, I would argue that I use 8 field lines to represent 1 microcoulomb charge, and these of course go on forever. I'm not going to draw them forever, but that's what's meant by the electric field. It's a representation of the force that a positive point charge would experience if it was placed at some location, and any charged particle is going to generate an electric field. All right, we started with that. We went from there. From a single charge, and then I started talking about plane of charge. So if we have a whole bunch of these charges all distributed in some fashion, such that, I'll go into a new slide, such that I had a plane of them that went on forever. And if I could rotate this in 3D, I can't do it quite so well in PowerPoint, but in a 3D rendering program I could do something like that, and you can imagine a plane that could rotate in any direction. And if this plane were completely positive charge distributed uniformly, then if I was to take a cross-sectional view of it, I'll rotate it as if I'm rotating it here. So in a cross-sectional view, the electric field is going to be directed away from the plane, because if you imagine the plane consists of a lot of positive point charges, and if this plane was infinite, or closer to infinite, these point charges would interact with one another, and so there would be no forces that are directed either up or down, because any force that's directed up by a charge down here would have a corresponding charge up here that's directing in the opposite direction. So any vertical components would cancel, but all of the horizontal components reinforce one another, which results in electric fields that are directed away from the plane of charge. And you remember the relationship for electric field associated with a plane of charge. I could insert it here in an equation. But for a plane of charge, the electric field is given by E is equal to the charge density, sigma. This is how I do equations. For those of you who need to do them, you can do them in Word. Divided by epsilon 0. Oops. There should actually be a 2 there if it's just a single plane. So that's the strength of the electric field, and the direction is that it's directed away from the plane of charge. And if I have 2 planes of charge that are of opposite sign, so if we have 2 planes of opposite sign but with the same charge density on them, you'd add the effects of this one plus the effects of this one in the middle, and the two would add together to result in, or to put a plus sign here, adding them together, I would get the expression that we've come to see more frequently. This one. The other two. Alright, so that's going to be the electric field strength in between two planes of opposite sign. So if I were to draw the electric field lines, I draw them emanating from one, going to the other, and of course the equipotential lines. Let me draw through these electric field lines. Something like this. Etc. all the way down to the bottom. And the equipotential lines would be perpendicular to those. So if I were to sketch those, it would look like this. In this case, let me change the color. Where each of these lines represents a different value of potential in this field. All right, so that's equipotential, of course. Potential is associated with the potential difference, where we're assuming zero potential to be somewhere, and in this case we would assume it to be on the negative plate. If the negative plate is on the right, then we would simply find the potential at any point in space in here by multiplying the electric field strength by the distance from the point of zero potential. If we have a point charge, going back to this case here, for point charge the potential is given by the expression kq over r. I'll insert an equation in here too. Looks better. K times Q divided by R. Of course, the electric field strength is given by K times Q divided by R squared for points. But in any case, that's what potential is given by, and I'm assuming that the potential is zero when I'm infinitely far away from this positive point charge, or for that matter, from the negative point charge. And if I want to determine the potential from 2 point charges, I would simply, at any point in space, insert a point here. Say I'm talking this point in space right here. Make it more of a point. At that point, I'd have to determine the distance from here to here, and then the distance from here to here, and those would be my corresponding r's. I'd put each q in the equation, determine the distance from there, find the potential at this point caused by that charge, and the potential at this point caused by that charge, add the two effects together, and I get my potential at that point in space. For electric field, as you know, I have to add them vectorially. Okay? So I hope this video gives you a little bit more of a review of the relationship between potential and electric field for both point charges and plane charges. Good luck.